to 2 pi directions. Okay? If you don't know what the Bessel function is, this is the Bessel function. Okay? I will not derive it, but it's derived in the textbook. In general, if you have a Bessel function of the nth order, you can show that it can be written in terms of integral summations of plane waves. Weighted by the proper thing. Okay, if you have this identity, then you have to weight with this coefficient. Okay, and that coefficient, that is actually not a function of alpha. This actually can be taken outside the integral, but this is a very important integral identity, which is derived in my textbook. You can only find this derivation, I think, in a much more complicated and laborious fashion in Whittaker and Watts, very old book. I don't know whether it's 1T or 2T now. Okay, Whittaker, maybe 2T's. I don't know which looks right. I don't know. Okay, maybe just 1T. Whittaker and Watts. So very old books on Bessel functions. You can find this identity derived there. But I think I derived it in a much simpler fashion. And this equation is very important for fast multiple. If you want to understand fast multiple, some of you who studied will come across this important integral identity. Okay? Because you're actually explaining cylindrical weight in terms of plane waves. Are there any questions so far? Okay, let's look at the point source. We have done the case of a line source. And we know how to expand the field due to a line source in terms of plane wave. And then we derive this very interesting integral identity. And how do we repeat this for a point source? You can go through the same exercise, actually very similarly. Apply Fourier transform theorem and so on. But let me try to do it with a slight twist. Instead of applying Fourier transform like I did before, I would like to apply Fourier transform from the very beginning, so that the derivation is somewhat different. So for a point source, we will have to solve this equation. The 3D Green's functions that hopefully Michael Chow has taught you how to solve this equation, which is the equation for the Green's function. And let me use a simplified notation for this. And let me use a shorthand notation for this. Okay, this is often represented by this. So let me use a shorthand notation for this, which is just that. Okay? And you know how to solve this equation. It gives rise to a spherically symmetric function, which is e to the I k naught r over 4 pi r, right? I think that's what you have been told. And all of you supposedly know how to derive this. I don't have to derive them. But let me apply Fourier transform to the entire equation. Okay? Let me use 3D Fourier transform to represent this field in terms of 3D Fourier integral. I will have dkx, dky, dkz here, which I will in the future just use a shorthand notation, write it as dk. And then if I write this as Fourier transform integral, I will have this very laborious looking exponential and then phi tilde kx, ky, kz. Okay. Then in the future, I will just replace it with e to the I k dot r, because this is actually just a plane wave. And in the future, I just replace this with k bar. Okay, to make the writing of things a lot simpler on the blackboard. Right? Then I don't have to write so many things on the blackboard. So if I now substitute this expression into the above, exchange the order of integration and some and differentiation. All the partial square, partial x squared, partial y squared, partial z squared become simplified because they operate on that. So I will do the above, substitute that in there, okay, and exchange the order of integration, and take this differential operator into the integrand, and I use a shorthand notation for this, and then this thing will just become minus k squared. It's actually kx squared plus ky squared plus kz squared. I just call it k squared. Okay, plus k naught squared. And then e to the I k dot r, okay, plus phi tilde of k. If I substitute that in there, and then the right hand side will be minus 1 over, let me put in the minus 1 over 2 pi cubed back in. And then the kx, the ky, the kz, right? E to the I k dot r. If I write down the Fourier transform integral representation of the delta function, that is it. Again, if this thing is complete and orthogonal, and this thing is complete and orthogonal, and this is equated for all x, y, and z, I can now remove the integral and equate the integrand. Don't always equate integrands. Equate integrands only if you can go through this argument that the integrand is multiplied by some functions that are complete and orthogonal. Okay, otherwise you will end up like a person who published a paper in AP transaction and make mistakes, remove integrals without justifying. Okay? Then, if I now equate integrand, I will have this piece being equal to that piece, and I will have a very simple equation. Minus 1, right? Yeah, minus 1. This should be plus. So I have phi tilde of k hat is equal to 1 over k0 squared minus k squared. The k squared is kx squared plus ky squared plus kz squared. Okay? And then I have a solution that I have obtained two ways. One is this way, and then another one that is obtained by the Fourier transform way. This must be true, and that this must be true. The triple integral dk here means dkx, dky, dkz. E to the I k dot r over k naught squared minus k squared. And this must be equal to e to I k0r over 4 pi r. It turns out that the integral on the left-hand side can be simplified further. I don't have time to simplify the integral on the left-hand side. I'll do that in the next lecture. And then come up with all these very nice identities like Will identity, Sommerfeld identity, all the identities that you find very useful in electromagnetics. And identities that are useful for you to understand a large number of physical phenomena. The super resolution evanescent wave spectrum. Why is evanescent wave spectrum is important? Because evanescent wave spectrum contains the high frequency component, but a high spectral component of the field. So you can harvest and capture the information in the evanescent spectrum. You can get super resolution. But the trick is how. Okay? So lots of papers have been written about it, but I think they're all very difficult to do. We'll talk about it next time. So